So let's take a look at problem number 2. It asks us the same things that it did in problem 1. Find the expression for build a new function fg using functions f and g, build a new function f over g, build a new function g over f. So from problem number 1 and from class, we know that this notation simply means to take f of x times g of x. So f of x is a fraction 1 over the square root of 6 minus x. G of x, I'll write it as a fraction, square root of 6 minus x over 1. So we can see that we have common factors in the numerator and denominator, and that this product is just equal to 1. Let's go ahead and do parts B and C. Now, this is the notation for f of x over g of x. We have a complex fraction within a fraction. Our numerator is a fraction. Now our denominator is just g of x. Our denominator is not. But we can make it a fraction by placing it over 1. So to do this division, we know that division is the same thing as multiplication of the reciprocal. So here's my numerator. I can change this division to multiplication if I take the reciprocal, if I flip my denominator. When you square a radical, the radical goes away. We have 1 over 6 minus x. Alright, let's continue with part C. This is just a new function that we could call h. The notation simply means to take g of x and divide it by f of x. So by substitution, I can replace this g of x with its equation, 6 minus x. And in the denominator, we get a fraction, so we have another complex fraction. Division is the same thing as multiplication by the reciprocal. So I have my numerator, and I can change this division to multiplication if I take the reciprocal. This is just over 1. You don't really have to write over 1. When I multiply these, the radical goes away. So there's my answer for part C. Now in part D, we want to find the domain of each of these. So let's find the domain of f, find the domain of g, intersect them together, and then also when we're finding the division, make sure the denominator is not equal to 0. So I'll need the domain of f. In the domain of f, I see a radical, a variable underneath a radical, and I also see that variable in the denominator. So I've got 6 minus x has to be strictly greater than 0. I can't allow it to equal 0 because it's in a denominator. So 6 greater than x, I like to write the variable on the left so that when I'm making my number line, that everything, that the arrow points in the direction that I'll shade my values. So the domain for f, I'm getting it to equal, since my arrow is shaded, negative infinity, and you never have a bracket around negative infinity. It's not a true number. It's not an endpoint. I can't include it in an interval. So my domain for f is all real numbers that are strictly less than positive 6. Let's erase this stuff. Let's move this up. Now let's consider the domain of G. In G, it's almost the same as f, but the difference being that the square root is not in the denominator anymore. So when I go to set up my inequality, when I was looking at f, since it was in the denominator, I said that it had to be strictly greater than 0. Now in the numerator, it can be greater than 0 or it could equal 0. And so when I solve for x less than or equal to 6, last time I did not include the number 6. This time I will, and shade all numbers that are to the left that are smaller than 6. In interval notation, that's from negative infinity up to 6, but now it's a bracket because it's including 6. This is our domain for G. Now our domain for the product FG is the intersection of these two sets. And if you draw a picture right next to them, 6 is excluded here, and 6 is included here. So 6 is not in both sets. So 6 is not going to be in my intersection. When I intersect the domain of f intersected with the domain of G, I get all real numbers that are strictly less than 6. So the domain is from negative infinity up to 6, but not including 6. Now they want me to find the domain of f over G. The domain of f over G is the domain of f intersected with the domain of G, but we have to make sure that G of x, since it's in a denominator, is not equal to 0. So let's focus our attention on this part, because we already know the intersection of f and G. It's up here. All real numbers that are strictly less than 6. G of x, let's set it equal to 0. Square both sides. Add x to both sides. So hey, x equals 6 will make G of x equal to 0, because the square root of 6 minus 6 is 0. We don't want that to happen, but the intersection of f and G, it's already excluding 6. So the domain of our division, f over G, is the same as negative infinity to 6. Now, let's come in and find the domain of G over f. Well, the domain of G intersected with the domain of f, just like addition, that that is commutative, the order of my intersection doesn't matter. If I intersect the domain of G intersected with the domain of F, that's the same thing as the domain of F intersected with the domain of G. But this time we need to consider if we have any new restriction with this function f being in a denominator, that it can't equal 0. But remember, f of x is 1 over the square root of 6 minus x. A fraction only reduces to 0 if the numerator is 0. Well, this fraction has a numerator of 1, and that's constant, and it's going to remain constant. So this f, this function, no matter what input you plug into the function, it will never have an output of 0. So it's not adding any restrictions. So our domain of g over f is the same as our domain for f over g. It's all real numbers that are strictly less than 6. So they asked us in part B to find the domain for part A, which was the product, the new function that was built from taking f times g, find the domain for the division f divided by g, and find the domain for g divided by f. Now it's possible that we may see problems where each one of these is a different domain, but for this problem they happen to all be the same. Hope that helps.